Okay, let's talk about rectilinear motion, which we actually talked about way back in chapter 2 when we were first introducing the derivative. We're going to talk about this in a little bit more detail now. So just to remind you what rectilinear motion is all about. This is when a particle moves back and forth in a straight line. And you might think, well, that's not very useful. But you'll see as you move through, your physics classes and in calculus 3 and stuff, how this stuff really does apply to when you're working in 3 dimensions as well, or really any number of dimensions. So if you can understand rectilinear motion, then you'll understand all kinds of motion. Anyway, so we're just going to work with one dimension in this class. Okay, if S, we usually use the letter S to describe the position of a particle. So that, in other words, that's its distance from some starting point at time t, right? So if S of t is the position function, then the velocity function is S prime of t, right? So the velocity is just S prime of t. It's the first derivative. And the speed function would just be the absolute value of the velocity function. So let's start off. Let's look at this example. It says, let's say that the position function is t cubed minus 6t squared. Let's say that's the position function. Find the velocity and speed functions, and then let's compare their graphs in Desmos. Okay. So we've got S of t equals t cubed minus 6t squared, and we're supposed to find the velocity function. Well, the velocity function is just the derivative of the position function, right? Which is going to be 3t squared minus 12t. The speed function is just the absolute value of the velocity. That would be absolute value of 3t squared minus 12t. There's not really much simplifying to do there. But let's look at the graphs of these things in Desmos. Okay, so there's the position function. I'm going to zoom out a little. Ooh, that dips down really low, doesn't it? Okay, and then the velocity function. Okay. So that's what the velocity function looks like. And then the speed function, of course, was just the absolute value of the velocity. Oh, it's not going to let me do that, huh? What if I say y equals, there we go. So there you go. That's what those graphs look like. Now, first of all, just comparing those two, right? The absolute value just takes all the negative stuff, makes it positive, which is why you get this little bend. But more interestingly, you can see that the velocity. Okay, so remember that. So the velocity is the derivative of the position function. The derivative is like the slope of the tangent lines. So you can tell that here you have a positive velocity, but the velocity is getting smaller and smaller as you approach 0. Right? In other words, the tangent lines here are really steep, but they get more and more shallow. Until you get to 0, the tangent line is just a horizontal line, in which case the velocity is 0. After that point, the velocity starts to get, the position starts to decrease, and so the velocity is decreasing as well. The speed is increasing, but the velocity is decreasing. Anyway, so you can see that here. So you've got a negative velocity at this point because you've got negative slopes to the red line. Like the slope of the tangent lines to the red curve, they're negative after that point, so the velocity is negative. But the slope is increasing in steepness, and so the speed is increasing, right? So you get an increase in speed suddenly. Anyway, so these things are just kind of interesting to look at and compare. We'll come back to them. Okay. All right. So the velocity of a particle is how fast its position changes. The acceleration of a particle is how fast its speed changes, or really a better, not its speed, but its velocity. So the acceleration of a particle is how fast its velocity changes. Okay. So that tells us that the acceleration function is going to be the derivative of the velocity function, or in other words, it's the second derivative of the position function. So again, let's say that our position function is t cubed minus 6t squared. Let's find the acceleration function, and we'll compare its graph to the velocity and position functions. So same position function, s of t equals t cubed minus 6t squared. So the acceleration function is the derivative of the velocity function, or the second derivative of the position function, if you like. Well, so here's the first derivative. So the second derivative here is just going to be 6t minus 12. Okay, so just a straight line. Let's take a look at that in Desmos. 6t minus 12. Okay, so here's something that I'll point out. Remember that the second derivative tells you about concavity. So when the acceleration function here is negative, that means you're concave down, right? So you're concave down from here until, here. And then after that, the acceleration is positive, and so you're concave up, right? So that's pretty interesting. So there are the three functions together. If you compare just the velocity and the acceleration, right, you've got the slope of your tangent lines are all negative here, but they're getting closer and closer to zero. Here they're equal to zero, right? So the acceleration function is zero there. And then here they become positive, right? And so the acceleration function is positive. So very interesting to look at these things all together. All right. So now note that a particle in rectilinear motion is speeding up when its velocity and acceleration have the same sign, and it's slowing down when they have opposite signs. Okay, so in other words, it's not just like if the acceleration is negative that you're slowing down. No, because if your velocity is already negative and your acceleration is negative, then you're going to be speeding up. You're just going to be speeding up in the negative direction, right? So a particle in rectilinear motion is speeding up when its velocity and acceleration have the same sign. They're either both positive or they're both negative. And then it's going to be slowing down when they have opposite signs. So moving ahead with the same position function, if s of t equals t cubed minus 6t squared, use the graphs of the velocity and acceleration functions to determine when the particle is speeding up and slowing down, and then we'll compare our analysis to the graph of the speed function, absolute value of the velocity. Okay. So let's go back to Desmos. There's not any work for us to really do on the paper, but we're supposed to use the graphs of the velocity and acceleration functions to figure out when the graph is speeding up and when it's slowing down. So again, it's going to be speeding up whenever the velocity and acceleration have the same sign. So here you have a positive velocity, but you have, so from I guess negative infinity to zero, you have a positive velocity but a negative acceleration. That means that you're going to be slowing down. Okay, so maybe we should write this down. So from, or maybe I'll say on negative infinity, here let's say this. So on negative infinity to 0, the velocity is positive and the acceleration is negative, so slowing down. Okay. From 0 to 2, so it looks like from 0 to 2, the velocity and acceleration are both negative. Okay. So you're speeding up. You're speeding up in the negative direction. Okay. From 2 to 4, so from 2 to 4, the acceleration is positive, but the velocity is negative. Okay. Okay, and then finally, from 4 onward, the velocity and acceleration are both positive. Okay, so now let's compare that to just what the velocity function looks like. So I'm going to ignore these things, okay? Or the speed function, rather. So here my speed is really large, but as time goes on, it's getting smaller and smaller and smaller and smaller, until eventually the velocity is 0. At that point, the particle is momentarily stopped. Then the speed starts to increase again, and it increases, increases, increases. Then the speed, so it decreases from negative infinity to 0. Then it increases from 0 to 2, right? Then it decreases again from 2 to 4, and then it increases again from 4 to infinity, just like we said, right? Just like we said. But and again, you can tell that just by comparing the velocity and acceleration functions. So that's kind of an interesting thing. Okay. So kind of putting this all together, you're probably coming up with all this on your own anyway, but let's just recall. Okay, so if f prime is positive, so in other words, if the slope of the tangent line is positive, then f is increasing. If the slope of the tangent line is negative, then f is decreasing. If the second derivative is positive, then f is concave up. And if the second derivative is negative, then f is concave down. So using that information, let's use this graph here. This is the graph of the position function s of t. This is a different position function now. Okay, but it says use the graph to determine when the particle is speeding up or slowing down. Remember, it's going to be speeding up if the velocity and acceleration are both positive or both negative. And it's going to be slowing down if they have opposite signs. But we can tell just by looking at the concavity where the acceleration is positive. When we're concave up, the acceleration is positive. So notice that we're concave up. We're concave up on 0 to 2. Okay. We're concave down from 2 to 1, 2, 3, 4, 5, 6. Then we're concave up again from 6 to 7. and then it's just a flat line from 7 on, okay? Now, what about the slope of the tangent lines, right? So here the slopes are positive. They're still positive. So they're positive from 0 all the way to 1, 2, 3, 4. So slopes are positive from 0 to 4. And then the slopes are negative. They're all negative from 4 to 5, 6, 7. Or I'll say on the interval from 4 to 7. Okay? Okay, so when are we speeding up? Well, it's concave up. So the second derivative is positive, so the acceleration is positive, right? So in other words, maybe we can do this. I'll make a little chart. So 0 to 2, 2 to 4, 4 to 6, and then 6 to 7. And we'll say velocity, acceleration, and then I don't know, I'll call it the conclusion, I guess. So this is our interval. So from 0 to 2, the velocity is positive, the acceleration is positive, and so the conclusion is that we're speeding up. From 2 to 4, we're concave down, or sorry, from 2 to 4, the slopes are still positive, so the velocity is positive, but the acceleration is negative, and so we're slowing down. Okay, from 4 to 6, the velocity is negative, and the acceleration is still negative, so we're speeding up. And then from 6 to 7, slopes are negative, the acceleration is positive, so we're slowing down. And then I guess from 7 onwards, right, from 7 to positive infinity, the velocity is 0 and the acceleration is 0, because notice that the position function, the position of the particle is not changing, and so we would just say the particle has stopped. Okay, so that would be that, right? So that's example 4. That's how you kind of analyze these sorts of graphs. It probably wasn't necessary to write down all this stuff. You probably could have just done the chart. That's a much better way to organize your thoughts, I think. Okay, but one more. So example 5 says, suppose the position of a particle is s of t equals 2t cubed minus 21t squared plus 60t plus 3. Analyze the motion of the particle for t greater than or equal to 0. So analyze the motion of the particle. What do they mean by that? Well, we can talk about the velocity and acceleration, of course, right? We can say, all right, so for example 5, we can say, well, s of t is 2t cubed minus 21t squared plus 60t plus 3. So the velocity is going to be 6t squared minus 42t plus 60. And the acceleration is going to be 12t minus 42. Okay, and maybe we want to find the critical values here. So like here, I know I can factor out a 6. And then I can probably factor that as t minus 5 and t minus 2, right? Here I can factor out a 12. can I factor out a 12 actually? 12 doesn't go into 42, does it? 6 does though. Okay, so I think I'm just going to make a chart kind of like I did before. So here I'm going to get a critical value at 7/2, or sorry, an inflection point, I guess, at 7/2. Here I'm going to get t equals 5, t equals 2. So so here I go. Here's my chart. So from 0 to 2, and then I'll have some stuff. 7/2 is like, it is 3.5, right? So I'm going to go from 2 to 7/2, and then I'm going to go from 7/2 to 5, and then I'm going to go from 5 to infinity. Okay, and let's analyze the velocity and acceleration in each of these intervals. So from 0 to 2, if I plug in a test point in there, from 0 to 2, like if I plug in 1, I'm going to get 6 times a negative times a negative. That's going to be a positive, right? So the velocity is going to be positive in that region. From 2 to 7/2, so 7/2 is again like 3.5. So if I plug in like 3, I'm going to have a positive times a negative times a positive. That's going to be a negative. From 7/2 to 5, like if I plug in 4, I'm going to have a positive times a negative times a positive. That's still going to be negative. And then if I plug in something bigger than 5, like 6, I'm going to have 3 positives will make a positive. So that's the velocity. What about the acceleration? So if I plug in something between 0 and 2, like 1, I'm going to have 2 minus 7, that's negative. If I plug in something between 2 and 3.5, like 3, I'll have 6 minus 7, that's still negative. If I plug in something between 3.5 and 5, like 4, I'm going to have 8 minus 7, that's positive. And then if I plug in something bigger than 5, like 6, 12 minus 7, that's still positive. Okay. So what does that tell us? That tells us that here we're slowing down. Here we're speeding up. Slowing down. And then speeding up. Okay. What else would they want us to do? So one of the things that they like us to do is to draw, like if you encounter this kind of question in the homework, one of the things that they want you to do sometimes is draw a schematic, which kind of tells you, it kind of shows you the motion of the particle, I guess. So you can kind of visualize it on a number line, I suppose. So we're starting at time t equals 0. And then we had some interesting things happen. Okay, so here you have the times when interesting things are taking place. It might be interesting to know what is the distance of the particle, right? What is the position of the particle at those times? So maybe I'll look at each of those, right? So like at time 0, for example. At time 0, we're 3 units from whatever the starting point is that we're measuring from, right? I'm just using the position function up here. So at time 0, so s of 0 is 3. S of 2, My goodness. Okay, S of 2 would be, let's see, 2 times 2 cubed minus 21 times 2 squared plus 60 times 2 plus 3. It's 55. At 7 halves, S of 7 halves, that's 41.5. And at 5, S is 28. Okay. So this allows us to, so I'm thinking of this as my position axis, right? So I'm going to try to map out how far the particle is from 0, with respect to time. So at time 0, we're already 3 units away. The largest here is 55. So trying to do this, maybe I can go by 5s. Let's say 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. Hey, that was pretty good. Okay. So we're starting here at 3. So we'll say, this is our starting point. That's at t equals 0, right? This happens when t equals 0. And then by the time we get to 2, we're all the way up here to 55. So this is at time t equals 2. So we're starting at time t equals 0, and we are increasing, right, because our velocity is positive. So we're increasing all the way out to 55. And then at 55, by the time we get out to 55, we're going to go backwards to 41.5, so that's maybe right about here. So this is at time t equals 7 halves. Okay, but our velocity is still negative, right? So our velocity is positive. That means we're moving in this direction. Then at time t equals 2, it turns around and we start moving backwards. After 7 halves, we're still moving backwards until we get to 28. Right, so 28 would be like right here. And then we turn around and come back this way again, forever. So this happens at time t equals 5. Okay, so this is kind of what a schematic would look like. And you could kind of label on there where you're speeding up and where you're slowing down. So you're slowing down this whole entire time, but you're kind of moving in this direction, right? But you're slowing down from here to here, you're speeding up from here to here, slowing down from here to here, and then speeding up after that. Anyway, so that's that. I think that's all I want to say about rectilinear motion.